Good, hello, good morning, everyone. It's a pleasure to have you here for the start of our industry communication and talks. We will have two talks this morning related to quantum key distribution. One from Tommaso Occhipinti, who is the CEO of Quantum Communications Italy, and one from Daniele Bonanno, Mercury Ltd. So thank you for accepting the invitation and come to interact, discuss, and present the work of, as Tommaso will say, a company that is collaborating with the Maltese quantum ecosystem. Thank you.
Thank you. Thank you very much. Okay. Hello, everybody. Today, I would like to show what we have done and what we will do, okay, with our company, which also may be interesting for you in the sense that we are the product as a company. We are the product of the Italian research, I can say, of the research, of the academic research. In fact, we are an official spin-off of the National Research Council in Italy. So think about making studies, maybe PhD, postdoc, and then decide not to continue the research, the academic research, but to create a company, so to become an entrepreneur. So this is my story, let's say, I mean, what I have said. I made my studies in Padova University. I am a telecommunication engineer, so I'm not a physicist. And my thesis and my PhD thesis were on quantum key distribution. So in old times, 2005, something like that. Okay. So I made some research. I made some couple of years of postdoc contacts with university. But later on, I decided to create my first company, which was not KTI, it was another one. It was Adaptica, related to adaptive optics, maybe you know the technology. It's a funny technology for increasing the performance of optical systems. Then, after 10 years of that company, which was a good success, we sold it completely to an international holding. And then after that, I created, together with other researchers from the National Research Council in Italy, this company, QTI. So sorry for this long introduction, but just to give also the perspective of a possible story related to quantum technology. Maybe if you have questions, you can make now or later after my talk, of course, and interrupt me whenever you want. I didn't check exactly with the bosses your knowledge on this kind of topics. So excuse me if I am too basic in the initial slides. I will go rapidly, okay, or interrupt me if you don't understand something. So in our opinion, we are not in the quantum revolution. We are in the second quantum revolution, in the sense that at the time we got the transistor, the microelectronics, the lasers, that were the real first quantum revolution. Then, after some decades, it happens that we are in the second quantum revolution, where we try to use the quantum states to create and manage information. Okay. Uh, you know probably better than me this slide, but this is how we see the world. Okay, we divide the quantum technology world into 4 topics, basic. Okay, and where we are here. I mean, our company is on quantum communication. So quantum key distribution is a sort of subset of quantum communication. Okay. Again, this slide probably you know already, but this is the slide. I mean, the content of this slide is what I use to sell. Okay, this is the point. Consider that I am the CEO of a company. A company must be alive. Okay, selling. Okay, the point is selling. So if I have to sell quantum distribution, I start from the threat of the quantum computer, which is, I mean, the quantum computer is a fantastic thing, fabulous thing, fabulous potentialities, but it has a threat on the security of information of the classical information theory, in particular of the cryptographic algorithms that shares cryptographic keys around computers, servers anywhere in the world. Okay, so it is, I mean, it is really easy for a quantum computer to break some public key algorithm, classic algorithm, to break them. Okay, theoretically, but we know that easily. I mean, in some few years, it will become available a computer that really, a quantum computer that really breaks not only in theory, but really the RSA, for example, algorithm. Okay, but the second point is something that we use, let's say, better than the first one to sell. Sorry if I stress this point, because the threat is also on today, not only on the future. If you are an attacker of an important data and you save the data that is, that is secure by standard cryptographic algorithms, you save, you take it apart, and you decrypt later with the power of the quantum computer is a problem, right? Today, think about the data of the long-lasting data. I make an example. The healthcare data in a hospital database. This is something that must be saved. In Italy, for example, there's a law that obliges the hospital to maintain the data of the patient for at least 10 years. 10 years is something that is compatible with the arrival of the computer, of the quantum computer. Okay? Or think about some financial data. A company moving money between nations, and this kind of data must be absolutely secure, not to give information to other competitors, for example. But this kind of information is crucial for that company, and they want to maintain it secure not only for 10 years, but forever. Again, this is another point. So, how to surpass, how to overcome on the quantum computer threat on the security of the information. We can do it into essentially 2 ways, family of algorithms or techniques. Okay, the first one is called PQC, post-quantum cryptography. So again, maybe I'm saying something easily for you. But I would like to stress the difference, but also the fact that they are compatible with the other technology, quantum key distribution. So PQC is the algorithmic way of creating an algorithm or some algorithms that are immune to the power of the quantum computer. On the other hand, quantum key distribution is the physical way to forget about quantum computing, to distribute keys with the rules of quantum mechanics and not with artificial algorithms that are created by the human being. So the cons of the PQC is that it might not be a definite solution, in the sense that any kind of algorithm maybe can be broken by a normal computer or by a quantum computer. On the other hand, QKD, just speaking about the cons, it's a system. I mean, it's a physical system. It has some hardware that at this time costs quite a lot. So quantum key distribution costs a lot compared to PQC algorithms. But the point is that you have to combine the two technologies to give a quantum secure ecosystem to the information technology society. What it means? It means that think about a bank. A bank has some physical places, some server rooms around Malta, for example, and there they have a lot of data that have to travel through optical fibers at high speed, and they must be secured by quantum key distribution, which is the natural way of securing that kind of data. But the same bank has to give you, to your mobile, maybe the PIN code for a transaction. In that case, it's easier to use PQC, because that one is an algorithm that works in any kind of network without any fiber. I mean, this fiber is fiber. It is a 5G connection. No matter. Okay. And what I'm saying is what is the trend right now. Also, some important financial institution, international financial institution, I can name JP Morgan. JP Morgan is sentencing exactly this point. They want QKD for data, massive data transfer, and they want PQC algorithm for the last mile, let's say, security to the for the mobile or for the ATM machines, for example. Okay. So I already said everything about this this slide. So the point is that in a security system, you needed to distribute keys. If you have symmetric keys, the perfect algorithm is already there. I mean, it can be used, for example, AES with 1K, 2K bits. That is fantastic. But you need the symmetric keys at the end of the communication system. So essentially, the modern cryptographic scheme moved the security problem from the encryption of the message to the distribution of the keys. And with the distribution, so the problem is here. And again, I already told you that the quantum computer can easily break some of the most used standard classical distribution system, keys distribution systems. So how can you do this? How can you secure the system with conventional key distribution based on the complexity, so the algorithms. And here you have two families, the current key distribution systems, which are not good, and the post-quantum, I mean, they are good today, but probably not in few years. And the post-quantum cryptography that are good also for the next years, but we don't know if someone from I don't know an adversary state understands how to break that kind of code. On the other hand, quantum key distribution with its complexity, which I will show you that is not so complex, can manage the distribution of the keys physically using the quantum mechanics. So just to come to approach the how we see the things. Okay, we have a place A here, a place B. You need with quantum key distribution, you need a channel, a communication channel where you make the quantum states traveling and the classical channel, normal classical channel, can be internet, can be any kind of communication channel. The quantum channel is a channel that is capable of getting these quantum states and bringing these quantum states to the end or to the other hand without altering them. So since typically the quantum states that are using are essentially based on photons, the perfect quantum channel is the optical fiber. But it's not necessary. You can easily use free space, for example. So free space is a channel, also for quantum key distribution. You let the photons traveling through air or through, space in satellite-based optical communications. And in that case, the quantum states are good. I mean, travels in a good way. Also in that case. You will see in a later slide that we introduce another quantum channel that is quite funny. Maybe you are interested because you live, some of you live in this island. The underwater optical channel. So we have a project with the Italian Navy where we are creating a quantum key distribution system under the water without optical fibers, but directly communicating with the quantum states between point A and point B under the water. Okay. You know the principles, but let's say the real point for quantum distribution is we encode information in a Bloch sphere. I mean, in a state that stays in the infinite position between two states, quantum states. We use the Heisenberg uncertainty principle and the direct consequence of the no-cloning theory. These three pillars are at the base of quantum key distribution. If someone wants to read your quantum message, it alters. This is basically the point. I don't want to annoy you too much on the real details of one of the most used quantum key distribution protocol. I don't know if you already have seen somewhere in some courses. We use, in QTI, we are using BB84. Okay, there's BN92, there are other. We think that this one is good for our technology. Okay, then there are some little modifications, okay, that I will show you later, but essentially is BB84. So how it is made our quantum key distribution system? The place A, is called Alice. There's the quantum transmitter, preparation system and transmitter. At Bob, at place B, there's the measurement system. So there's the single photon detector. I mean, before there's the essentially the beam splitter of the BB84. The essentially there's an optical processing. We use an interferometer practically. And then there's the time tagger. I mean, I'm sorry, the single photon system, the single photon measurement system that is based on two single photon avalanche diodes. And then there's the time tagger, which counts exactly the time difference between one arrival time and the other arrival time. Oh, I must tell you that when you implement BB84, you can decide how to create your quantum states. Many of other companies or research-based institutions use the polarization of the light, I mean the single photon polarization as a quantum state, okay? We prefer not to use them. We use the time beam encoding. So essentially is a phase difference between single photons. So this is why we need at the receiver an interferometer to understand if the photons constructively, I mean, collides or not collides, and we see it using the BB84 algorithms. What is the case, you ask me, or there are the many papers? So time beam encoding BB84. This is the technology of quantum of QTI, quantum key distribution. Just a practical advice, I mean not advice, note is that here there one key technology. I mean, they are all key technologies, but one is really at the basis, or it's really important. It's the QRMG. So it is the source of entropy. So you have for the good BB84, you need a real source of random numbers. So we use the quantum random number generator. We have one that we buy from another company, and it is based essentially on optical properties. Okay, there are other kind of things. For example, ID-Quantic uses some kind of a mixture between. I mean, they are more electronic properties. We use the optical one. Okay. On the other hand, all the things here are important as well, but the key component and probably the most problematic because it costs a lot is the single photon detector. I mean, we use them too. We use two single photon detectors. And these kind of things that are small like this cost something like 20, 25 kilo euros. Okay, so just to tell you what it means. Okay, the technology is moving, is advancing, but there are few companies creating this kind of single photon avalanche diodes. There are other technologies, but cost more than this. For example, the superconducting single photon detector. So with QKD, as I already said, we have to deal with the cost of the technically we can call it bill of material. When you create the machine, you have the things to buy, you have to do something on that, and then you get the power. Okay? The bill of material costs a lot. So, coming back to the story, we created the company in 2020 in Florence. Today we have two branches in Florence. One is the headquarters and design center. The other is the production. It's in Florence, in the city of Florence. The other place where we are is a marketing and business development headquarters that is in Rome. Because in Rome, you know, there are the institutions, all the big companies, so we prefer to stay there. Okay, this is the story of the company. I don't want to annoy you, but maybe this kind of, I mean, that kind of logo, you know, is a Telecom Italia. So it is the largest telecom operator in Italy and one of the largest in Europe, in the world. So they invested in QTI. So the big difference between QTI and any other kind of company, apart the Swiss guys that are owned by the Korean telecom operator, QTI is the one that have a huge industry behind. Now at the moment they own, I mean, TIM owns 80% of QTI. So really they decided to invest a lot on the company because they think that this technology is at the core of their business proposition. We work on all the quantum channel, okay, easy. I already told you. And these are our products. I don't want to say too much on them in the sense that I'm not selling to you, okay? But that one is the quantum key distribution Helix, that's the identically that's the Bob, two rack units of device, okay? This one unit is the brain, I mean, more not the brain, but is the key management system. So when you have the keys created by QKD and you want to make a complex network, not single point-to-point networks, you need a quantum, we call it quantum key management entity. We use a key management entity instead of key KMS, which is key management system, because KME is more related to the standards of ETSI, because we use ETSI standards to do all these kind of things. And the last one is an additional software package that stays here to insert all these kind of things into software-defined network, software-defined networks, which is the golden standard right now in telecommunication networks. So now I have not so much time, but I have a lot of slides showing things, I mean, what we have done. I can pass very rapidly, if it's okay. Okay, I mean, because I finished the introduction, I mean, the technology introduction and the story of the company, but maybe it's interesting for you to see what okay, no more than 5, 10 minutes, no more than that. So, this was an international experience that we have done in 2021. It was the first three-nation quantum key distribution system implemented during a G20. Okay, I mean, if this one was not easy because of two motivations. The technology at the moment was, you know, so and so, because we were really at the beginning, first. Second, logistically it was a mess because we were making something that stays for the G20, international meeting for something like 10 days. And we have to make this between three telecom operators and 3 nations. So it was not easy. Consider also that we had a so-called trusted node in Ljubljana. So because there was no connection between Trieste and Ljubljana, sorry, not Ljubljana, Postumia was the trusted node. There was no physical direct fiber between Trieste and Ljubljana. So we had to implement a trusted node. So with all this kind of complication at the time, but it was a success. And also the links were not so easy. There was a 20 dB of losses in Trieste to Rijeka. These are quite close, but the losses were quite high, but still was working. You have the reference but I can leave this kind of slides. This is another interesting thing that we have done in 2023, for example, was the first quantum key. When I say first, it is really the first, in the sense that no one showed quantum key distribution in a military base in the United States. I mean, probably they already have quantum key distribution, but we don't know, okay? But commercially, or I mean, with an Italian company, no, with the company not based in the United States, it was really the first time that someone was showing to the Air Force, in that case, quantum key distribution capability. This was really interesting because the European Commission asked us to make a multi-vendor quantum key distribution in a digital assembly in 2023, so last year. And again, in this case, there was a link, there was a trusted node in the between. This was Alice, Alice, and Bob. This was the trusted node. And the two links were made by QTI on the right and the Lux Quanta on the left. Lux Quanta makes quantum key distribution in a completely different manner, which is the continuous variable quantum key distribution. It's another way of reading it. Okay, we are quite friends with them because we are not in direct competition. There are other kind of enemies for us, which are using, for example, the Swiss company that I was mentioning. But it was a success. This one is, I just mentioned because at our knowledge, it was the first time that we were making a remote industry 4.0 machine actions. Do you know what is industry 4.0? I mean, it's the new perspective of making industry big production facilities where machines do everything, and everything is remotely controlled by an edge server somewhere, not in the factory. Okay, so in that case, an hacker can make a big problem if it enters into the information system of the factory. So this was a practical, interesting application that we have done in the city of Torino, because Torino in Italy is very related to automobile, to the car production. This was another one, but this one I can skip. It was made in Naples, in Italy. This slide I would like to show you because it's more, I mean, it's a really telecommunication oriented, I mean, telecom operator oriented, but maybe some of you knows about the big company Cisco, which makes the big, let's say, big apparatuses for classical optical communication system for telecom operators. And in this case, we were creating keys for a top product. I mean, the top product line of Cisco. Okay, and this machine, which is the NCS 1004, this is the one, is capable of making uh, four. I think it theoretically can reach 1 terabyte or 1 terabyte, 5 terabit per second of cryptographic data traveling to a core of fiber. Only one core of fiber, they have 1.5 terabit per second of data, encrypted data into that core. So in the same core, there were our little quantum states traveling together with the 1 terabyte of data. Now, in that case, it was 300 gigabytes, but I mean, the same mass, okay? So it was really a success, and at the base of, I mean, at the concept, as a consequence of this experimentation, we have a partnership with Cisco, and we are proposing this kind of solution to telecom operator because really demonstrates that QKD is compatible with the normal optical communication networks. We made also the recent G7 in Italy with Meloni and Biden and all those kind of guys. Skip. Okay, we are approaching the free space channel in the sense that we, as a researchers, also me, in the past, we worked only on free space channels, but as a company, we always work in fibers. Now we are moving also on free space because in some application it's required also the atmospheric free space propagation channel. And here you have these are our, this is our headquarters in the Istituto Nazionale of Optics in Firenze, and that is the physics department of the Galileo Galilei in Arcetri. This one is the project that I mentioned, you know. I can't tell too much because it is under the supervision of the Italian Navy, but the final target is to make ultra secure communication between a submarine and one or a fleet of automatic underwater vehicles. Okay, here the problem which is the coherence of the quantum channel. You send quantum states into water and you have a big problem. So probably here the maximum length will be between 50 meter up to 150, 200 meters, something like that. But still is interesting for the Navy. And I would like to conclude with an experiment that we have done together with Malta. To be very precise, we were just a part of a big project, partially financed by NATO, but essentially we made a 100-kilometer quantum key distribution implementation between Pozzallo in Sicily and Malta using an underwater fiber. This is the reference of the paper. If you want to look at it, it was quite easy, let's say, but we were using the single core of the fiber to do everything. So also the service channel, the communication channel. So it was interesting. If you want to read it. Thank you.
Thank you, Tommaso, for the presentation with all the projects and the 2KD free space. And so there we have time for two quick question.
Yeah. I already have microphone. I would just ask a quick question. So the only thing I don't really understand is like in the sense that the non-entanglement based QKD methods, they kind of still, if I'm not the one producing the devices, I will basically have to trust the source does what you promise that it does. And if I'm a receiver, I don't know, it's kind of like against my, let's say, cryptographic principle to do so. So why choose a non-entanglement based method?
This is an interesting question. Thank you. Let's do like that. If you want to do entanglement-based QKD, you have to make a higher level of complexity in the deployment first, because it's a different source, it requires different, technologies. Let's say we have the entanglement source in our lab. I mean, if it is necessary to do that, but we made a real precise decision to do without in this period of time. The golden standard, together all the producer of QKD system and also the customers, is this kind of things. Think about also European quantum communication infrastructure, big project in Europe. They really are pushing the faint pulses, let's say. We can discuss about what you mean, but we have also some, let's say, security proof on our system. Okay, so if someone of the customer are asking something like you said, we give to them, okay, this is our security proof. Okay, you have to trust me on the source, but even if we have a pulse with 5 photons, what happens? Here is written what happens. Okay, it is essentially mathematical demonstrated, and also physically we have some apparatuses or systems just to overcome some of the typical attacks on the faint pulses, the theoretical faint pulses attacks. You understand what I mean? Okay.
So let's thank Tommaso Kippint again, and further question, we put them on the coffee break. So our next speaker is Daniel Bonanno from Mercury LQ. Exactly. Sorry.
Okay, so good morning, everyone, and thank you for having us. And thank you, Tommaso, for the excellent presentation. So I'm Daniel Bonanno. I'm from Mercury Cybersecurity. We're a small startup based here in Malta. And today I'd like to talk to you about QKD from a network's point of view. So Tommaso already kind of hinted at this. QKD between point-to-point links is, all well and good, but in order to make it really useful, we need to kind of create these networks between different countries, different cities, so on and so forth. Similar to Tommaso, I'm not a physicist, I'm an engineer, so this might be a different perspective to what you're used to. So if I get any of the physics stuff wrong, there's Andre somewhere over there. He's a physicist, CEO of the company, so you can ask him. So to start off with, why do we need QKD, right? And to kind of answer this question, we need to start from the beginning. So in today's world, most of our stuff is digital. It's online, right? Banking, health, everything is digital essentially. And we encrypt data because we don't want anyone else to read what's being sent. Okay, so essentially encryption algorithms would garble up this data so that no one else, without having the key to ungarble it, would be able to read what there is. But without authentication, we can still modify that data. So authentication essentially verifies that whoever sent this data, is who they say they are, and it wasn't modified in between. Okay, so you should never use encryption by itself. Essentially, you should always use what we call authenticated encryption. So they should always be used together to ensure that you have the best level of security possible. But does this mean we are safe? From classical computers, yes. Right? So classical computers do not have the computational power at the moment to break current encryption algorithms. So we are safe. Okay? But are we safe from quantum computers? Realistically, the simple answer is no. Right? So you can think of quantum computers as Alan Turing, right? So Alan Turing broke the Enigma code, and we know the repercussions of that. Quantum computers are the same with classical algorithms. They will be able to break them, as we've seen in the previous presentation. There is Shor's algorithm, which reduces the time it takes for a computer to crack certain codes exponentially, right? So we aren't safe. And the threat is there now because of the store now and decrypt later attack vector. So what is QKD? QKD is one of our kind of saving graces in this scenario, okay? So you might have seen in some films or something, you have a guy with a handcuff, some luggage handcuffed to his hands to deliver keys between two locations. Okay, QKD essentially is that guy. Okay, it gives us a way to generate two identical pieces of information, in this case, the keys, between two different locations. And there's a theoretical proof which states that only the two parties which were involved in generating this key have the information about this key. Okay, it wasn't messed. It wasn't read in transit because of the no cloning theorem. So it's backed by the laws of quantum physics. So no technology today or in the future, even technology which we haven't thought about, can crack QKD. Of course, if it's implemented correctly. That's why we say theoretical, because of course, then there's the physical aspect of it, which, if it's not done correctly, can leave certain backdoors. So QKD essentially requires an optical medium and makes use of photons to transmit bits, which we will then use to form our key. Okay, as we've seen, it can be set up over fiber or a free space link, but the important part is that there are no active components due to the laws of quantum mechanics. It can be done over fiber, but it's not really feasible. That's why we tend to use fiber optic essentially. So you also have probably heard about PQC, post-quantum cryptography. So QKD and PQC aren't really enemies, as some people might have you believe. In fact, we firmly believe that they need to be used together, right? So with QKD, it's proven theoretically that it's secure, right? What PQC tries to do is it's mainly software based, and it tries to do what we are doing nowadays for classical computers. So create algorithms which are computationally hard even for quantum computers. Okay, so it's a software only solution, making it much cheaper than QKD. So on your phone, you're most likely not going to have QKD, but it's very likely that you will have or already have PQC. Okay, so we're seeing certain companies already shift towards using PQC algorithms for user-to-user communications. All right. So with QKD, we know that the range is somewhat limited, but with PQC, obviously, you have a much larger range since it's only software-based. Here, we need to be a bit careful because there were, for example, NIST finalists, which were said to be quantum safe, but essentially then the algorithm was cracked using classical computer in a few days. So PQC, we think it's safe, it might be safe, but we still don't have that heritage to ensure that it actually is safe. With software-based solutions, we tend to need that to ensure that our algorithms are safe. So where you require extremely secure communications, which last for a long time, so you need to store your data securely for a long time, QKD is the way to go. Okay, but in certain cases, PQC is required because you cannot do without it. You cannot have QKD on your phone, at least not right now, right? So that's where PQC comes in. In certain cases, for example, for authentication, PQC might make sense as well. There are ways which you can use QKD, but you can also use PQC to provide like an extra layer of protection. So what's on the market? Essentially, there are two kind of types of QKD, particularly DV-QKD and CV-QKD. As Tommaso said, they aren't really in competition because they, kind of have different advantages and disadvantages. So really, it's tailored to what you need. All right. So with DV, you have much longer distances, but CV-QKD is more noise tolerant. So if you have a link where it's particularly noisy, CV-QKD might be a bit better. CV might be a bit cheaper since it uses telecom grade detectors, but with DV, you have, for example, the ETSI protection profile. So someone, for example, asked about how can we trust the device does what it does. The ETSI protection profile is the closest thing we have to kind of certification nowadays, right? So that is only true for DV-QKD. So essentially, there's also that pedigree that, the device actually does what the manufacturer says it does. Apart from that, DV can also be a bit, in terms of maturity, it's a bit more mature, whereas with CV, it's still a bit newer, I would say. There's also entanglement-based QKD, but it's still a bit, in the early stages, but we're getting there as well. So what if you want to make use of QKD at home? What if I want to try it out? What if I want to get my hands dirty with QKD? Can you really use it? Well, realistically, no, right? You cannot, you can, but it costs a lot of money. You need to have fiber, you need to buy these devices. So realistically, it's a bit difficult to try it out at home. But yes, you can, if you're emulating it. So at Mercury, it's on our GitHub page, we have an open source ETSI 14 reference implementation. Essentially, it's the standard interface with which our kind of software intends to get keys from these devices. So it's free on our GitHub page. You can just download it, and it will give you like an emulated QKD pair, which you can then kind of use to get your hands dirty with software. So it's exactly the same interface. It's literally a plug and play solution. So if you're using the reference implementation, you can unplug it, plug an actual QKD device, and the system should work the same way, right? In fact, it's what we use to develop our software. So that's kind of the introduction about what QKD is and why we need it. So moving on from point-to-point links to more mature QKD networks. So to create a network, we need infrastructure, right? And there are two ways you can go about this. You can either use existing infrastructure or build new infrastructure. Now, with existing infrastructure, there's less expense. So you don't need, to dig up new fiber so that you create these QKD links. You can use what's already there. And this, of course, means you have a faster time to market. You're using infrastructure which is already there. With new infrastructure, it's yours. So you can do with it what you want. So if you want to use dark fiber because you'll have less noise, you can do that if you build the infrastructure yourself. So in a way, it also simplifies vendor selection because certain vendors allow for less noise or more noise. Of course, again, they are kind of the opposites of each other, right? So with existing infrastructure, you might not have access to dark fiber, therefore your vendor selection is limited. Apart from that, not all paths are passive. So we said that you need to have no active components in the link. So, if the existing infrastructure doesn't allow for that, what can you do, right? You cannot just remove these active components just because you want QKD, okay? So although newer infrastructure is less practical, sometimes that might be the only way to go, okay? So with kind of determining whether existing infrastructure is feasible to use for QKD, there are certain parameters which you need to assess. So this is usually done per link on a per manufacturer basis. Okay, so depending on what the noise on the link, the manufacturer which you're going to be using for QKD, you can assess whether that link is suitable for QKD or not. Apart from that, there's also the wavelength. So traditionally, and this is how it is nowadays, QKD is done on the C band or on the O band. So different manufacturers can either have, we must use this particular frequency, it depends on the laser, or we operate on this whole band, or our lasers are adjustable and can switch from one band to another. So again, it depends a lot on the manufacturer and what is already on the existing link, and also the transmission medium requirements. So do we have lit fiber, dark fiber? How many channels are already on the link? Can we coexist with them? And all this stuff would of course affect the key rate which is being generated by the QKD devices. Right? So there's Raman scattering, stuff like that, which will affect the loss and the key rate. So why are we talking about QKD networks, not QKD links? So we know that QKD range is essentially limited. It is what it is. How do we expand that? So because the range is limited, there are options on how we can expand this, particularly satellites, quantum relays, or trusted nodes. Okay, so in order to be able to achieve larger ranges, we need these networks. Okay, so one way to do this is by making use of entanglement-based satellites. So what you have is a satellite which has an entangled source, and we have two locations. And essentially, since the satellite isn't fiber, it is able to see a much larger range. So this is one way with which we can increase the range of our QKD services. Now, in this case, the satellite, of course, doesn't have any access to the keys, and post-processing, which is processing to generate the actual keys, is done at the sites. So there is no computational complexity at the satellite itself. But again, we still need to be in range. So there's still limitations in terms of range, and we tend to have lower key rates, right? So with satellites, there's a lot of loss. Work is being done to address this as well, but we still have lower key rates. It might be fine for you, but for certain applications, it's not enough. Another way to increase the range is making use of quantum relays. So QKD security essentially is due to the fact that we have the no cloning theorem. Theoretically, this is possible. Again, I'm not a physicist, but we're not commercially there yet. So quantum relays, although these will work in theory, in practice, they won't work. So the alternative is making use of trusted nodes. So in terms of range, trusted nodes are the alternative to quantum relays. What happens is you have one node, a node in the middle, and another node. So A, B, and C. A and C aren't connected together, but they're both connected to B. So we trust B to give us a key, which we can use between A and C. Okay, now there are different ways to do this. I don't believe any one of them is secure, more theoretically superior, theoretically more secure. There are some practical security, which comes into play. So in practice, there's some stuff that you would do just because it's better in practice. It makes it a bit more difficult for an attacker to get a key. And obviously, it depends a lot on the key management architecture which you are using. So when we're talking about quantum networks, we need a key manager to access the keys and manage the keys. Depending on how you design it, it might, be beneficial to use one way or another to implement trusted nodes. So essentially, what would happen though is that when you introduce a trusted node in the mix, you're also increasing what we call the attack vector, right? So you have another entity which is joining the party, which essentially means that you are increasing the range where someone might be able to attack and try to get the key. Okay. However, as we said, this is something which is required for quantum networks. If I want to speak with someone who is in, I don't know, Brussels, I most likely won't have a direct link. So we need to have trusted nodes in place, which you can only get by having quantum networks. Okay. Now, as I said, this can be done with satellites or without using satellites at all, just using normal QKD devices. So starting from the very beginning, how do we implement trusted nodes? It's all based on the binary XOR. So the XOR, or exclusive OR, essentially works as follows. So you have, it takes 2 bits as an input and provides 1 bit as an output. Okay. If it's 0, 0 or 1, 1, so the same bit at the input, you will get a 0. If it's differing bits, you get a 1. Okay. And this is the interesting property which makes trusted nodes viable, right? So if I have the same bit at both inputs, I will get a 1. Yeah. And if I XOR it with B, I will essentially get B. So this is what would actually happen. So imagine you have 3 sites, A, B, and C, right? A and B have key AB, B and C have key BC, and we want to get a key between A and C. In this case, we'll use B as a trusted node. So B would XOR K, AB, and KBC, the 2 keys it has, which would result in KAB XOR KBC. It would then send it to C. Now remember that C has KBC. We XOR it, and this results in KAB. So the same key which is between A and B. So we've managed to establish a key at both A and B, at both ends, which is the same. Again, using B as a trusted node, since obviously B has the same key. Okay, so we need to trust B to not leak the key. Okay. Now we can also use satellites as a trusted node to even increase the range. So you can use multiple nodes, so not just a node in the middle. So you can have trusted nodes composed of multiple nodes. So if you want, you can have A, B, C, D, and E, which obviously increases the attack vector, or you can also use satellites. So in this case, the satellite is acting as the middleman. It would generate a key with A, then move and generate the key with C. Okay, so it's the same concept. However, we have this moving satellite, which essentially is not distance bound, so we can reduce the number of nodes which we introduce, and it's much simpler, right? However, again, it has access to the source, and in this case, the post-processing is done on the satellite, so it requires more power. Okay. If range wasn't a problem, why not have a full mesh network? Why do we need trusted nodes? So with a full mesh topology, every node would be connected to all the other sites. So trusted nodes wouldn't be an issue. Okay. The problem with this is it's very expensive, and apart from that, as soon as you add another node, think of all the connections which you have to add. All right. So it's very unlikely that your infrastructure will allow for this. Just to give you an idea, with 4 nodes all connected together, you have 6 links. right? 3 at each point. With 5 nodes, that increases to 10 links, 4 connection points at each node, and -1. With 20, you need 190 links, which realistically, you won't be able to get, especially on existing infrastructure. Okay, and this is how it generalizes. As you can see, it will be, as soon as the network starts growing, it will be impossible to keep up. And that is why essentially we need trusted nodes. In networks, you also need key management systems, right? So key management systems or key management entities are vital. So they do not only manage the keys, ensuring that a single key is given to a single application, right? But they also make sure that in terms of trusted nodes, there is coordination, because obviously you need to coordinate where you're going to get the key from, okay? Apart from that, you need network control. So in this case, one way to reduce costs is by multiplexing. So if you have a transmitter, why not use it with 2 receivers, with 3 receivers, right? So there's ongoing work on this to try and reduce the cost as much as possible. So if I want to communicate with 3 locations, I wouldn't need 3 QKD devices. I'd just use one and multiplex in time between them. So in this case, mainly for DV, the receiver is easily costlier, right? So you have one receiver with multiple transmitters. So if I want to speak with, let's say I'm a company and I have three sites, if I want to speak with all of them, I'd just have one receiver, I'd be the receiver with 3 transmitters at the other end. Now, again, the network control obviously would help the key management to kind of determine which link needs to be switched on and switched off, depending on what keys are needed where. And it needs to be done on a per need basis, right? You cannot do this often because of calibration. Calibration takes time, we're time multiplexing, so we don't afford switching constantly because it would cost us a lot of key material. Some European manufacturers actually do offer this, but still early stages, so work is being done also in this area. Apart from that, you can treat, QKD networks as normal networks, and normal networks need monitoring, need alerting. So if you have a network, you cannot just assume that it's working. You need to make sure that it's working, right? If, I don't know, there's someone who cut the fiber accidentally, you need to be alerted to this, right? So in fact, at Mercury, we've developed a dashboard. Those are actually 3 locations, which we have actual QKD devices here in Malta, and this is kind of monitoring them. So we're monitoring link loss. So as you can see, the link isn't super stable, but it's quite stable in the sense that there is some jitter in terms of loss, and that obviously affects the key rate. Okay, so if you have more losses, key rates will be lower. That's mainly it from my side. So that's a QR code to our GitHub page if you need access to it. Also, Prism is a project which we're working on as Mercury, one of the projects which we're working on. It's part of the EuroQCI, so the European Union has this push to build these infrastructures. Prism is Malta's EuroQCI, so if anyone's interested in that, I can happily give you more information. Thank you.
Thank you, Daniel, for the wonderful presentation and for the great work done by the key actor in the Quantum Maltese ecosystem. We have a time for the short question.
Hello, thank you for the presentation. Last year in 2023, there was a paper that showed that Shor's algorithm cannot, in fact, break any encryption. If there is very small noise, like it says vanishing small noise. So from that point, if that paper is correct, then both quantum computers can't achieve what we want them to achieve, which is break encryption, in which case then there is no need to create new encryption methods. So my question is, what is your opinion on that? Because I don't think we will be able to reach noiseless quantum computers ever.
So really it's based on, having noiseless quantum computer, as you said. So I haven't actually read the paper, but it would be interesting to check it out. Essentially, we cannot account for what might happen, especially because, as we said, the data nowadays is still it still needs protection in the future. So if for some reason there is a noiseless quantum computer, we cannot leave ourselves exposed. So if I'm storing the data now, and for some reason we do manage to achieve noiseless quantum computers, or there is, we say in quantum computers, what if there is an exponential increase in computational capacity, right? So algorithms can still be broken. The only reason why we are safe is because we don't have the computational power.